Okay, just hold on a second. Okay. All right. So right now we are gonna start off with electric fields, and Munib is also here. Okay. All right. So first off is the electric field. Electric field is basically defined as it is a region where a charge feels force. This force can be of attraction or repulsion, both. I need to remember that. So when it is a positive isolated charge, I just want to tell you that the field lines will go out from a point, and that is why it is called a point charge, because it's like, it seems like the fields have originated from a center, like that. And then you got, like, if it's a positive negative charge, then obviously the field lines are gonna go towards this, like this, and towards a single point. Now, so the question is, what does the field lines really represent? Okay, and why are they always going out from the positive and in from the negative? The reason for this is that these depict the direction of force on a stationary, you can also write isolated, positive unit charge. Alright, so it's like wherever the positive will go or feel the force, if it's stationary, or I mean it will feel the force this way. So that is the direction of the field. Like, for example, if you look at here, if I keep a positive charge right here, then obviously it is going to go away from the positive isolated charge because they repel each other. And then if I place it here, so it's gonna get attracted to the negatives. That is the reason why the field lines are made like this. All right, is there any question? Please let me know. All right, interesting. Now, so the next question is that what exactly is electric field strength? Electric field strength is defined as force per unit positive charge. The symbol of electric field strength is capital E. The SI units of this is like Newton per Coulomb, and it is a vector quantity, which means it will have a value. Also, it will have a direction. Now, so you can write electric field strength as E, which is force per unit charge, and that would be the formula, like that. Now, If you have any questions, please let me know. Okay, so I think we got everybody except for Abdul Moiz. Yeah. Okay. Alright, should I go forward now?
Yes, sir.
Okay, so now we got uniform electric field. Um, Uniform electric field is basically like, again, you should remember that if it's between two parallel plates and one is positive, let's suppose one is negative, then the field will go from positive to negative. The general rule is that the field goes from a higher potential to a lower potential. And then same goes here. But what you notice right now is that the lines in the first diagram are more than the lines in the second diagram. And there are a couple of features that I want to talk about, and then we're going to know why it is so. So first of all, we should understand that all lines between the plates are straight. So they do not show a curve. It's just at the end, because that's not between the plate, that's just at the edge that they show a curve, otherwise they're just straight. And then the second thing you should remember is that they are all equally spaced. The third thing you should remember is that they have a constant electric strength at all points within it. So that's why it is called uniform electric field. Now, when you basically draw anything, you should remember that the electric field lines, I'm just going to write a note here so you guys remember. Field lines, oh, that's the wrong spelling. Field lines always enter and exit the surface at 90 degrees, which means they will be out at 90 and they will be in at 90. So you should always remember that. The other thing you should remember is that the strength of electric field lines show the strength of electric field is shown by the density of lines, which means that obviously this diagram has a greater value of E. And the reason is because the lines are close, the electric field strength would be higher. Is it clear, everyone? Okay. So we can always write it is depicted by how close the lines are. So that's pretty much it. Now, when you're looking at something like this, you should remember that suppose you have an electric field, one plate is like 20 volts and there's one plate at negative 20 volts. So if you draw a potential graph, you'd realize that if this was like initially there was a charge that was right here, so it had 20 volts of electric charge, and then when it reached the other plate it must have an electric voltage of like minus 20, and exactly at the middle right here where the voltage is 0, this is the line which is at the center, right? So this is the center of the plates. So that would mean that this is like the 4 centimeter, because the total plates are 8, and that position would be the 8 centimeter. So it's exactly at the middle you will have potential 0, and the line would go like this. Now the thing is that you might realize that basically this particular value, if you find the gradient of this line, like if I find the gradient like this, so the gradient will give me a value of change in voltage over change in distance, and it will be negative. The reason why it is negative, because the line has a negative slope like this, a gradient. So this basically represents electric field strength. So this is the reason one way of defining electric field strength is that we call this as also known as the negative potential gradient. So that would be the one of the features of uniform electric field and how electric field behaves with respect to potential. Alright, so if you have any question now, please let me know. Okay, pretty good. Fahar Arsalan and Suman, Gatika, Juweria, Tanjim, Triple N Gaming, Rafe. Everybody understands this? Anushe and Aman
Yes, sir.
and Ahmed. Okay.
Yes, sir.
Pretty good, right? Now, I hope you guys have drawn it too. So then we can move forward. Interesting. Alright, so going to a question like this. In this question, alright, this part we're gonna do later. So for this one, I'm just gonna give you this part as homework, which you can complete later when we cover this up. But for now, we're gonna look at this particular design. Okay, Javeria, I'm sorry. You can write it down. So from March start, because I just want to be sure that we finish the syllabus in time. So I would probably increase the timings of the class, and the class might start like half hour before our regular time and finish at the same time that it does. So if you guys have any issues, you can always private message me so I can inform the academy to be aware of that. Anyway, so for this one they have shown two parallel plates, and one plate has a positive potential, one has a zero potential, and they say there's a distance d apart, and basically, alright, Javeria. So then it says plate A is earth and plate B is blah blah blah, show the variation. So you guys should remember, because it is a parallel plate system, so when it has covered distance d, the line should be like starting from here, and at d it should just be a straight line and it should be 0. How do I know it is 0? Because when any particle is going to reach this plate like here, so it will have 0 potential. That is why I've drawn it like that. Alright. So by knowing this, we can always find electric field strength, which is negative potential gradient, and we can always find it like this. So it's pretty easy that way. It was in AS before, but now they started giving it in A2. They completely removed it from there, so you should be aware of that. Anyway, so then we're going to look at the acceleration in an electric field. It is pretty simple because we've just learned that electric field strength is given by force per unit charge, and we also know force is given by MA. So what we can do is we can actually put MA right here. So electric field strength will be equal to MA over Q, and then you can make acceleration the subject. So acceleration will be E times Q over M, and that's what we're looking for. So I'm going to write it a bigger one right here. A equals to E times Q over M, like that. And then let me just tell you what these are. So A is the acceleration, E is the electric field strength, Q is the charge, and M is the mass of that charge. So you should remember that. Okay. Like that. So it's fairly simple. There's nothing complicated in it. You just need to put in like E is equal to F over Q, and F equals to M is a very common formula. I don't think you will be able to forget it, so you shouldn't. Okay. Alright, Tanjim, do you understand that? Alright. So now I'm gonna go a bit forward, and we're gonna learn about Coulomb's law. Coulomb's law is quite simple. It will have basically it comes for 2 marks. So the first part of Coulomb's law basically states that it is the force of attraction or repulsion, alright, between 2 charges is directly proportional to the product of their charge. And the second part of this definition is, and it is, we're talking about the force, inversely proportional to the square of distance between their centers, like that. So what it means is that this is the distance r and the product of this is like this. So what they mean is that the force here is directly proportional to product of charges, and the force is inversely proportional to the distance between their center. This is also called the inverse square law. Alright, so do not worry if this word comes up. It's the same thing as the square of the distance between them. So when you combine this, so you would have to add a constant which is k, and k is not a real constant at all. We just call it like an electrostatic constant, and it has a value of 8.99 times 10 raised to power 9 Newton meter square Coulomb minus 2. As far as I remember, k is not given in the data sheet, but actually k itself comes from 1 upon 4 pi epsilon, where this epsilon is basically called, this is the real constant, and it is called permittivity of free space. It basically means if we create an electric field in vacuum, so how permissible the vacuum is to create or let the charges create the electric field. You don't need to go into other details. It just has a value of 8.85 times 10 raised to power minus 12 meter cube minus 3 kg second for ampere 2, so you don't need to remember the units as well. However, this red value is, I'm pretty much sure it's given in the exam, so you don't have to really check it. So but the difference is that this creates two formulas, and this would be F equals to Q1 Q2 over 4 pi epsilon times R square, but that's actually the same whether you remember K or 4 pi epsilon. It's alright, you will get the same answer at the end, so you don't have to worry about that at all. Alright, so you can write this down, please. I just want to tell you that all the other laws like Newton's third law applies here, so which basically means that if this was a positive charge, this was a negative charge, or vice versa, whatever force is felt by one, that would be the same force that the other feels. And the reason is that due to Newton's third law, the action and reaction forces would be the same. So the force on both of them will be same no matter what their charge and what their mass and what their distance is. So basically, it's just action and reaction in that sense, alright? Okay. Should I go forward now, everyone?
Yes, sir.
Okay. So then we just need to derivate the electric field strength with respect to what we've learned just now. Because the formula that we've learned before is that basically it covers only the uniform part of the electric field strength, but now we're going to learn about how if in non-uniform we can find electric field. So first of all, the formula we've learned is that electric field strength is given by force per unit charge, and force is given by K Q over R square. Now I've intentionally written capital Q and small q because between these two formulas there is no difference. This is just a way of writing, differentiating that there are two charges, right? So either you can use this or that, it's alright. And then what we're going to do is we can write F is equal to EQ because I can multiply Q on that side, and here we can put it equal to F equals to KQ over R square, and then we put forces equals, so it will be EQ equals to KQQ over R square. Since this Q and that Q cancels out, that would mean that electric field strength will be equal to KQ over R square. This is a general formula to find electric field strength of an isolated sphere at any point, right? Now, electric field strength obviously can be tricky in the sense that it might give you negative, positive values. So you always use negative sign for charge in for a negative charge, all right? and vice versa, right? So you can also use positive for positive charge. Usually they would not put you in that trouble, but however they can also give you in terms of epsilon, so you should not worry if they give you like 1 upon 4 pi epsilon times q over r square. So basically this is the same formula, there's no difference, one is in k, one is in epsilon, so everything is good here. All right. Okay, if you have any questions, please let me know now.
No, sir.
Okay, then going forward, we're going to learn the definition of electric potential at a point within the field. And is mass of charge the same as given in the formula sheet? Mass of charge. Mass of electron is given, Javeria, not mass of charge. So charge could be many electrons joined together. That could be a charge. Mass of proton is the same, yeah. Anyway, so then going to electric potential at a point, this definition is also of 2 marks. So we're going to learn the first point. The first point is writing work done per unit positive charge. So when you write that, you get 1 mark, and then for the next mark you got to write in moving. You can also change the word in bringing this charge from infinity to a point within the field. Okay, now writing within the field is not important. If you just write infinity to a point, that's enough. You can get away with that. Potential is a scalar quantity, and the SI units, like you know from the definition, it should be joules per coulomb because work done per unit charge, and joules per coulomb are also volts, so that would be the units. So according to definition, then the potential should be work done over charge, and you should remember that. Now, considering this, we can also write it in other form, like for a non-uniform field, because we know that potential is given by force times the distance that we're looking at over charge, because work done is force times distance, right? That's why. And since force is given by kq over r square, so we can plug it in. By plugging it in, then voltage is going to be kqq over r square times r divided by q. And if you notice right here, you might realize that there are 1 r here, so I'm going to cancel this with the square here, and this charge gets cancelled by this. So ultimately you are going to get voltage equals to kq over r, just like this, right? So just remember that that's the formula that most of the time you're going to be using. Now there are 2 more things that I would like to point out, and that is basically number 1, you should always remember, I'm just going to move this a bit up because it's taking a lot of space. The first point I would like to add here is that the charges move from higher potential to lower. So that's what you should remember. And we can earth, because earth is something that balances the charges, so we can earth to make potential 0 in certain things, so you should remember that as well. All right, If you have any questions now, please let me know. Interesting. Now, so keeping that in mind, then we are going to talk about null point, and then we're going to talk about we're going to draw, when we draw the graphs, I'm going to show you what exactly null point means. Right now, you should remember that the null point is a point where net electric field strength, when I say net electric field, because it is a vector, which means at this point the vectors are like opposite and of the same value, so that would make the electric field strength to be 0. Okay, and interestingly, I just want to add up here that this point, this is only possible between two like charges, and you're gonna see why in a bit. Alright, so you can write this down, please, and then we're gonna go forward. Okay. Okay. All right, should I go forward, please?
Yes, sir.
Okay. So now I just want to tell you, when you're drawing potential graphs, these are very, very important actually. The whole topic depends on them. So between two positive and negative charges, the field looks like this. So they connect from positive to negative and they go like this. Now you notice that I've drawn equal field lines on both charges. So whatever is coming out of positive, the same number of lines go in the negative. So you should remember that. So first we're going to draw potential graphs, and for the first one I should remember that if I'm going this way, like towards the right, then the field is going to decrease like this. How do I know it is going to decrease like this? Because the reason is that actually potential is proportional to 1 upon r. Since potential is like k q over r, so v and r are just inversely proportional, and this is the graph how you draw inversely proportional. So as you're going away from positive, the potential is decreasing, and it is decreasing inversely like this, right, as you can see. But as it reaches like negative, so if the charge is going towards negative like this, so you should understand that the negative potential is going to increase. So let me just use a different color. So the negative potential would look like this. Do you guys understand that? So it's basically, as it approaches negative, it's getting more and more negative. Understood? Okay, so Anusha, Ahmed, Arsalan, Fahar, Kartika, Juveria, Mukshik, Nadia, Usman, Tanjim, Triple M Gaming. Do you guys understand everything?
Yes, sir.
Yes, sir.
So now if we add them, like if we add these two fields, and what would be the result of this? The result would be the net field that we're going to draw. So what happens is that this blue line is going to reach 0, and then when it becomes 0 potential, right in the middle, somewhere in the middle, because they could be different, but if they're same, it will be right in the middle, and then the potential is going to get more negative, so we just added them together. Basically, they never get like, let me just put it this way. So basically, they never get, the one field goes like this, the other one basically stays like this. But when you add these two, every point on the line is added with every point on this line, so it gives you this graph. So this is the net graph that you should understand. Is it clear?
Why does it become more negative for the negative sign?
Because if the charge was here, right? Because it is closer to this, so it's right now at positive potential. As it is moving this way, so it is approaching the negative, right? So
Yeah.
suppose Gathikite was like plus 50 here and negative 50 here. So when it was at plus 50, you drew it like this. And as it goes in the middle, there will be some point at 0 volts, which is right here. And then as it goes on further, it will become more negative. Do you understand like that?
Okay, sir.
Yeah, so you should remember that. Now, if you realize this, you will basically see that we have just learned previously that actually the electric field strength is negative potential gradient, which means that if I try to draw any gradient on this line, because this is a curve, I need to draw tangent, so the potential, like the electric field strength will be maximum here, and then it is reducing, but none of the points it is 0. Every point has a slope, which means in this one electric field strength will never be 0. And the reason is because the field here becomes, it's never 0 anywhere around this. Do you understand? So we could say electric field can never be 0 in the in a field where two charges are unlike. Do you guys understand this? Alright, so then we're going to move to the next graph, which is this one. And because this graph basically shows you that this is like sort of, two positive charges, and because they're two positive charges, it would mean that this side, as you approach like this way, right? So it means that the potential is going to get more lesser as you go away from this. And then when it enters the field of the other positive, the potential will become more like positive again. So it becomes less positive and then it becomes more positive as it approaches another positive charge. So that should be your, thinking about it. Is it clear, everyone? Okay. All right. So then we're gonna go forward and see if we add them together, what you get. So actually what happens is that when we add them together, the net field is sort of like this. So I'm just gonna draw it for you. So the blue goes like this, and I don't know what that color is, but whatever that color is, orange maybe, so it goes like this. So when you add both of them, you might realize at this point they have the same value, and when you add, the net field is like this. This is the net actually that we need to draw. Like the other two lines are not important to draw, but it's just for the reference. And then if you basically draw a line, suppose if you want to draw a line like this, so you might realize that actually at the very center, which is basically this point, the line is getting less and less steeper, and it becomes completely flat here, which basically means at this point electric field strength has to be 0. And the reason why it is 0, because at this particular point the gradient is actually 0. And basically my other line is not very correct. Let me just fix that. I don't want this line. It should meet this line right here actually. Alright, is it clear everyone? Now please have a look at it and draw this. This is very important. While I'll check with who did not get it, who's alive. Okay, Javeria, everything is clear. And Arsalan, Nadia, Tanjin, Ahmed Squares actually. Okay, Aman, everything is okay. Yeah. And Mokshit, do you understand?
Yes, sir.
Very good. Now considering this, basically, these two are very similar. Like if you go away from this, like you're going in this direction again, if you go away from this, obviously the potential is going to get less negative, and then when you are reaching the negative charge, the potential is going to get more and more negative again, which means that if you add them together, which makes one line like this and the other line like this, and obviously the net graph will be like this. So it will all happen basically in the negative section, because both charges are negative. And obviously if you draw sort of line here, a tangent, okay, that tangent is not straight, so I'm going to draw it with my hand, okay, like this. So at this particular point that you see right here, the electric field strength is again 0, and the reason is that the gradient is 0. And from the diagram itself you might see that both of these graphs, exactly at the center, there is no field that exists. So which means that this point, like this point, is the null point, and this is also the null point. And that's why I wrote the null point can only exist when two charges are like charges, because they basically are repelling each other. And when they're repelling each other, at certain point in the middle, somewhere in the middle, they're going to have equal and opposite forces, which are going to ultimately cancel them out. And then if you place a charge there, it would feel no force because the net force will be 0. Is it clear, everyone?
Yes, sir.
So keeping that point very clear in your head would help you, write, if they ask you this, in a clear, concise manner. Otherwise you will be just digressing a lot, and I don't want you guys to do that. So make sure your concepts are very clear about that, when and how it's going to be a null point at the middle, somewhere in the middle. All right, okay, if you've drawn this, I would like to move forward then. Okay. All right. So then the thing is, when you learn how to draw graphs of potential, you can then draw the graphs of electric field strength. Okay. So it's sort of, a derivative of the potential graphs, right? So for example, in the first one, we drew a graph like this. And in this one, we drew a net graph like this. And in this one, we drew a potential graph like this. So you should remember which graph is what. Now going to the first one, we're going to derive what's going to happen. Like I said, at this point, the potential, if you draw a gradient, the gradient will show you a maximum negative value, which means that now you're gonna draw electric field strength at the start will be maximum, and then at this point, which is right in the middle, the gradient is like the shallowest, which means it's the less steepest. So it means that this point will be right at the bottom, because the gradient the electric field strength at this point is the lowest. And then at this point, the electric field strength, again the gradient is increasing, so electric field strength will increase again, and then it would be here again. So electric field strength would be basically like this for these graphs. Do you guys understand this? So I could just point out, like from a different colors, that this point is, let's suppose, A, this point is B, this point is C. So that would mean this is A, this is B, and this is C. And the line, just remember that line never touches 0, because electric field is never 0 in this part. Alright. Now, if you argue why the electric field strength is the least, so you can always look at the distance between the lines. So line spacing has increased, which means the density of the lines is less, which means at this point, obviously the electric field strength is going to be lower with respect to these and these, because they're closer to each other. So you can always, think like that as well. Okay. Okay. Everybody understands this? If you have any questions, please be very frank and be active and ask me, because I can explain that to you. Now, one thing that you should remember is that if you look at this graph, you might understand that all these lines that I've drawn have a negative gradient, because all lines are like this. They all are negative gradient, right? And because they're negative gradient, that is the reason, because electric field strength basically is the negative potential gradient, right? So which means that if you're getting a negative gradient out of the graph, it would mean that electric fields, this negative and negative will cancel out. Electric field will be positive at all points, and that is the reason we have drawn.
Sir,
Yes.
your voice is lagging.
My voice is lagging? Oh no, that's not fair. Wait a second, huh? I need to use.
Also, the audio of the mic changed.
Audio of the mic changed? That's not fair.
Like, it's different, your voice. It was clear earlier, now it's like muffled.
Okay, I'm changing the internet.
No, now it became okay, your voice.
Okay, is it fine now? Okay, cool. Okay.
Yes, sir.
Sorry about that. I'm just traveling. I'm at my cousin's place in Karachi. So in Karachi, internet's very poor. I don't know why. Alright, so now let's go forward and check the next one. So now you might realize that in this section we're gonna see that there is a negative gradient, and at this point there is 0 gradient, and at this point it is going to be a positive gradient. So when...
Sir, your voice is lagging again.
Oh no. Wait a second, please.
Sir, your voice is lagging again.
Okay. Never why would you not do this? Oh, now I understand. Okay, please hold on for a moment, okay? Let me put my phone on the charge. It's not like. Okay. All right. Wait a second, please. I just need to change the internet. Okay. Oh, please connect. That's not fair. Okay, Manal, could you please wait like 2-3 minutes more? We're just starting, okay?
Okay, sir.
Okay. All right. I'm really sorry about that. I've restarted my phone. Probably there was an issue. So, is it okay now? Guys?
Yes, sir.
Okay. So, what I'm saying is that basically these graphs, like you see, because they have negative gradients, so now the graph would be something like this. It would reach 0 and then it will go like this. And the reason is because obviously this point, if I say this is A, if I say this is B, this is C. So this is A, highest gradient, and then B, and then this would be negative gradient, so like positive, so we drawn negative. And at B, because electric field strength is 0, and this is the null point, so that is the reason why it is showing like this. Alright, is it clear, everyone? Alright, the last graph would just be the same, just flipped. So which means that now it would show you something like, you know, the opposite, which is if this is A, that's B, and that's C. So now the graph would be going like this to 0 and then like this, because this is the point where electric field strength is 0 and that is the null point. And both A and B, A has some gradient and C has gradient maximum, so that's why line is this highest at those ends. All right, if you guys have any questions, please let me know here. Okay. Okay, so I believe, yes. All right, like that. Okay, so